All right, finishing up chapter 6 then, let's talk a little bit more about gravity. So for now, what we've been using is when we talk about gravity, we talk about the force of gravity. We say something like this, right? The force of gravity is just equal to mass times the acceleration due to gravity, which we know in our case, here on the surface of the Earth, little g is 9.8 meters per second squared, right? So the problem with this, though, is this does not work if we want to talk about, orbits, right? Which is kind of what we're working up our way up towards. So, for instance, you can imagine, the moon is in orbit around the Earth is in orbit around the sun, so on and so forth. Um, but if I go to the moon, right? I've told you little g changes, right? When you're on a different planet. So I go to the moon, little g is about 1.6, but obviously it's definitely not, the Earth still has some force of gravity that's pulling on me, right? The Earth still has some force of gravity that's pulling on the moon. Otherwise, the moon wouldn't stay in orbit. Um, but obviously, when I'm at the moon, little g relative to the Earth, right? The Earth still has some force of gravity on me. I am not accelerating towards the Earth with an acceleration of 9.8 meters per second squared, right? So I am still within the Earth's gravitational pull, but obviously the force of gravity on me is much less because I have moved further away. So the actual formula for gravity, the most general formula for the force of gravity that we're going to use, discovered by Newton, can be written like this. It's capital G, which is a constant. I'll tell you what that is here in a second, times the mass of one object times the mass of another object, right? These are two objects, right? That you just need any two objects with mass will have some sort of gravitational force between them, divided by the distance between their centers of mass squared, right? R squared is what we call it, just the distance between their centers of mass. Um, so this constant g is a constant of the universe. It is 6.67 times 10 to the negative 11th, and the units would be um, newtons meters squared per kilogram squared, right? So essentially this is just kind of a measurement. We know that the force of gravity, we get stronger gravity when we have more mass involved, and we get weaker gravity when we have greater distance involved between the two objects of interest. And this capital G, this constant here, is basically just kind of a thing. The universe doesn't know what meters and kilograms are. The universe just knows how strong the force of gravity is. So this is just kind of a conversion constant to kind of um, bring us in towards, making sure that we're working in newtons, meters, and kilograms for what we're used to, right? But again, there's just some sort of constant we have to multiply it by to get these units to work out nicely for the units that we're used to dealing with. But again, kilograms and meters and then newtons, right? The universe doesn't know what those are, but those are the units that we use. So this G helps us make sure that we have the right units. So how do we get between these two different things, right? We know that this one's been true, right, the whole time. So how is this? Do we reconcile it with this one here? How do we have these two formulas end up being the same? Well, so again, as I said before, this is the most general formula. This is the one that we've been using. So let's look at why we're using this, like under what conditions is this one valid. So let's take a look at this. If I look at myself standing on the surface of the Earth, I can use Newton's law of gravity. And I can say, okay, I have G times mass of the Earth times my own mass divided by the radius of the Earth squared, right? Again, this is the distance squared. This is the distance between the centers of mass of the two objects. So the distance from my center of mass to the Earth's center of mass is essentially just the radius of the Earth, right? I mean, I'm a little bit less than 2 meters tall or whatever it is. So it's not really going to matter. It's not really going to make a difference for my height above the surface of the Earth. So we can just use the radius of the Earth itself. So this works out to being what? Sorry, I don't want to say this is equal to. Let's just take a look at these three terms that we have here. So we know G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Then we have times my mass. I'm not going to worry about this. So we need to have this kind of reconcile with this equation here. So if I multiply these three times the mass of the Earth, 6 times 10 to the 24th kilograms, then I divide it by the radius of the Earth squared, which is about 6,380 kilometers squared. Plug this all into your calculator, and what you'll get is about 9.8 meters per second squared if you do all your unit conversions and cancel everything out correctly, right? So essentially what we're saying is, this formula really was this formula the whole time, right? But it was actually this m times little g is what these three numbers happen to work out to when you're standing on the surface of the Earth. So yeah, so these are again, this is the kind of just the most general equation that you can have. So you can calculate what the force of gravity is between the Earth and the Moon, or between the Earth and the Sun, and so on and so forth, right? You have to know the mass of both objects and then how far those objects are away from one another. Okay, so we know then, of course, it is this force of gravity that's keeping these objects in orbit when we talk about these orbits. Let's take a slight pause from this gravity stuff and let's talk about some rules of these orbital mechanics, and we can kind of see how we get to doing some of these extra problems that we have, kind of tying everything together, where we'll look at our forces, we'll look at our force of gravity, and we'll kind of use that along with what we know about uniform circular motion to actually be able to derive some pretty neat things about just our solar system, our planet, and as we'll see, our galaxy as well. Okay, so we do need to take a look at this idea of Kepler's laws of orbital motion. So, a guy named Johannes Kepler, back in the, I believe it was 1500s, studied the planets as they moved around the sky a lot, and he was able to discover actually three different laws that all applied to how the planets move in the sky and how he believed they then orbit the sun. But as it turns out, he did such a good job that his laws are actually can be applied to any object orbiting any other object, right? So let's take a look at this. Kepler's first law is this: orbits are elliptical, right? So what do we mean by elliptical? So an ellipse is essentially an oval type shape, but there's kind of some certain rules to it that we have to follow. So if I draw my ellipse, it looks roughly like this. And the two defining points of an ellipse are the two focal points of the ellipse. And so the way you can define this, you can say the distance from one of these focal points to any point on the ellipse plus the distance from the other focal point to that same point on the ellipse is a constant value if you add these two distances together. So just as an example, right here, I have a distance. If I draw my my ellipse from here to my line from here to here, this distance from this focal point and this distance from this focal point is a plus b, right? So here's distance a, here's distance b. If I add a plus b together, I can pick any other point on the ellipse. Let's pick, I don't know, this point over here. So this is some other distance c. This is some other distance d. So as you can see, obviously, this focal point is not the same distance to everything on the ellipse. This focal point is not the same distance to everything on the ellipse. But this distance, a plus b, right, has to always be the same as the total distance to any other point on the ellipse. So the way you can kind of imagine drawing this, the book has a good picture of this. If you take a piece of string or something like that and nail it down to your paper, and you kind of stretch that string out with your pencil and kind of draw this oval shape that comes out of it, you will be drawing an ellipse, right? This total distance from focal point to the point on the ellipse and plus the distance from this focal point to the point on the ellipse, that total distance stays the same, right? It's kind of like how, again, if you nail down your piece of string, the length of the string stays the same the whole time. And so you will, if you stretch that string out and and just push it out as far as you can, you will be drawing this oval shape. As it turns out, a circle is a specific type of ellipse, right? And that would be one where you just have the focal points are directly on top of each other, right? So if you draw your circle, now you have one focal point here and another focal point here, then obviously, you just have the radius of your orbit of your circle around like that. So the shape of the orbits are elliptical, and the sun. So this is if you're talking about the planets anyway. The sun is at one of the focal points. So the sun is actually not at the center of the orbit. The sun is actually offset by a little bit. So if we talk about the planets going around the sun, The orbits of the planets are elliptical. They are actually, though, very, very close to circular. This was kind of a big point of contention for a long time in astronomy. Um, Basically, right up until Kepler had the idea of making these orbits elliptical, everyone had thought that they were circles. They were very close to circular. They are very close to circular orbits, but they are slightly elliptical, right? And so that kind of makes a big difference. And you do put the sun at one of these focal points, right? Um, so yeah, so again, then we can say, all right, looking at Kepler's second law, orbits are elliptical. We can also say objects in orbit sweep out equal areas in equal times, right? So they sweep out equal areas in equal times. What does that mean? We kind of, again, we need a nice picture to kind of really draw this. So let's say we have our ellipse like this. Um, I'll put the sun, say at this focal point, right? So if I have something orbiting the sun in this manner, and I wait, say, 1 week as it passes towards this close side of the sun, I wait 1 week and say it covers this distance, right? It moves from here to here. So that's 1 week. There is some area that it sweeps out if you draw your imaginary line from the object to the sun, right? So it sweeps out this amount of area. However, if I also wait a week at any point in this orbit, this total area has to be the same. So let's go around to the opposite side, right? So if I go around to the opposite side of the orbit, I wait 1 week, this area here has to be the same as this area, right? So obviously I'm much further away from the sun at this point. But if this area has to be equal to this area, the implication is that when we are further from the sun, when we're further from the object that we're orbiting, right, as we take this elliptical path, sometimes we're closer, sometimes we're further. As you are further, you are also moving more slowly, right? So that's kind of what this means. We have this idea of equal areas and equal times. But the knock-on effect of this is you are moving slower when you are further from the object you are orbiting, and you're moving faster when you are closer to it. This one is actually very easy to observe in your everyday life, right? How can you do that? Take your pen and throw it up in the air right now in your room. What happens as you throw it up? Right, so let's say, what you're really doing is you're essentially throwing the pin into orbit around the Earth. And as it moves further away from the Earth, or as it gets higher in the air, it moves more slowly. As it moves back towards the Earth and it falls back down, it starts to pick up speed. Now, of course, you're not going to be able to throw it fast enough. Your orbital trajectory will intersect with the surface of the Earth, which is just a fancy way of saying it's going to hit the ground, right? But so you do have this case here, right? It's this exact same physical phenomenon. When you have these objects in orbit, it's gravity that's pulling the pin back down to the Earth. It's gravity that's causing objects to orbit one another, right? So again, you throw your pin in the air, it moves slower at the top of its arc, and it moves faster as it comes back around. Now, of course, when you talk about these orbits, and you do have these objects that are not colliding in with the object that they're orbiting, right? You have, say, it's some sort of comet that's on this highly elliptical orbit. It goes out really far, it moves really slowly. As it comes back in, it swings around really fast, and then it moves more slowly, right? And this, of course, if you just follow what the force of gravity is doing, this should make sense as well, right? Gravity is constantly pulling this object towards the sun, right? Or towards whatever it's orbiting, right? So as it moves towards it, now it's accelerating towards it, right? It's falling down towards it, but it misses, it swings around. Now it's moving away from it. Gravity's pulling it back, so it is slowing down, right? So this is all we're saying with this not Newton's second law. Kepler's second law is this idea of sweeping out equal areas in equal times. So for us, though, the most important one that we're going to work with, understanding these is very important to kind of conceptually build your idea of how these orbits work. But the one that we're going to do the most math with is Kepler's third law, where he said this: p squared is proportional to a cubed, where p is the period of the orbit. So basically just how long it takes to go once all the way around your orbit. And a is the average distance to the sun or to whatever you're orbiting, right? So in the case of the Earth, right, what's the orbital period? It's 1 year. Um, what is the average distance to the sun? It's about 93 million miles or 150 million kilometers, right? And so what he said was that there is this relationship, this mathematical relationship between the orbital period and the average distance to the sun. Specifically, what he wrote, you can say p squared is equal to c times a cubed, where c is just some constant, right? And he knew there was some sort of constant value. He could calculate what that number was, but he didn't know where it came from or why that number was what it was, right? He just said p squared does equal a cubed, um, and it's there's this proportionality constant between them, but he didn't know what that proportionality constant was. He didn't know, as far as he was concerned, he did not know what that constant was, right? He just knew that there existed this direct relationship between the orbital period squared and the average distance of the sun cubed. So essentially what we're saying though is basically the further out you're orbiting, the slower you have to, the slower you need to move in order to maintain an orbit, right? In order to not actually fall in towards the sun and have this unstable orbit. So if you need a stable orbit, just make sure you follow this relationship here, right? This p squared equals a cubed. However, now that I've told you everything there is to know about Newton's law of gravity, we've talked about uniform circular motion. What we can do is we actually have the tools. We can do better than Kepler. We can do what Newton did, and we can actually calculate what this constant is. How would we go about doing that? Well, let's take a look at some planet that is in orbit around the sun. So let's draw it like this. Here's our sun. Here's our orbital path for some planet. As I said before, they are very, very close to circular orbits for all of the planets. They are not quite circular. They're slightly elliptical, so there is a small variation. But if we approximate them as circular, Kepler's second law will then also tell us, right, if our distance is the same from the sun the whole time, or very close to the same, then our speed will also be the same. And so if we approximate these orbits as circular, which is a good approximation, we can then apply what we know about uniform circular motion, right? We can say, okay, assuming this planet is moving in a circle, it's moving at constant speed, we can do some Newton's laws analysis of this and figure out what that proportionality constant is in Kepler's third law, right? So this is my velocity, and then I know I have some sort of force of gravity pulling me in towards the sun, right? And so if this is my free body diagram, I guess I don't really need, this V isn't really a force. I'm just drawing it to make sure we understand which way we're moving. But if I'm drawing my free body diagram, the only force would just be this force of gravity, right? There's no other significant force acting on this planet. And so then if we're undergoing uniform circular motion, what we can say is this. F of g equals mv squared over r, which we know we can say is g m over r squared equals mv squared over r. So this is our Newton's gravitational constant. This is, in this case, this is our mass of the sun. This is our mass of whichever planet we're talking about. This is also the mass of that same planet. This is the orbital speed, how fast it's going in the orbit, and then this is the distance, right? So let's go ahead, let's solve for this speed, right? So these masses will actually cancel out. We can then say v squared is equal to, we actually also have a factor of r is going to cancel out. So v squared is going to be equal to gm over r. So this is actually us, we are working our way towards Kepler's third law, right? We want to figure out what that proportionality constant is. Kepler's third law, though, was written in terms of what? We have the period squared is equal or proportional to the average distance to the sun cubed. Well, this r will be what our distance is, right? But how can we rewrite this v? What is the speed of this planet? We know that it's going to be 2 pi r, the distance that it travels in one orbit, right? The circumference of the circle, 2 pi times r is the distance, divided by the time that it takes, right? Distance over time is our speed, which is then, of course, just going to be p, right? The period for one orbit all around. So this is what our speed is, 2 pi r over p. So with this, we can then write 4 pi squared r squared divided by p squared equals gm over r, right? So with this, we can then rearrange, and we now have it, right? So this r we can multiply here will be r cubed. This p we can move over. This g and m we can divide. And sure enough, what we end up with is p squared is equal to 4 pi squared over gm r cubed, right? And so this is it, right? This is Kepler's third law derived with only using Newton's laws, right? Newton's laws of motion, his law of gravity, along with the forces that we had used from our previous chapter. So it was actually a big deal when Newton found this out, right? So both he and Kepler did arrive at the same result, and they arrived at it from two completely different directions, right? Kepler just observationally looked at the planets orbiting the sun and said, this stuff must be true. Newton, on the other hand, was able to show saying, okay, if this is how objects move around, let's build up from the bottom, right? And this law also still comes out from Newton's laws, as well as just from the observational evidence that Kepler had looked at, right? However, this is very important, right? What is 4? 4 is just some constant. What is pi? Pi is just some constant. What is g? G is just some constant. However, what is this? This is the mass of the sun, right? So we can rearrange this equation, and we can also write this. You can say m is just equal to 4 pi squared over g p squared times r cubed, right? And so this is actually a very useful tool for allowing us to measure the masses of these very large objects. If I find a planet orbiting a sun or orbiting any sort of star, any object orbiting something else, and I can measure its distance and I can measure its period, I can immediately calculate the mass of that object, right? Assuming it's in a circular orbit, right? Which again, for the planets orbiting the sun and for the moon orbiting the Earth, they are all very close to circular. So we have this case here. So whenever someone says what the mass of the sun is, right, whenever you hear that, or the mass of the earth, or even the mass of the moon, or any of these very large objects, we didn't like fly a scale out there and put them on the scale, right, obviously. But this is how you can get an estimate for what their masses are, right? And kind of start to get an idea for what the scale of these different objects are. If you plug all this stuff in, what you'll end up with is the mass of the sun is about 2 times 10 to the 30th kilograms. So this is actually a very useful tool. This is still used in astronomy today. When you're trying to measure the mass of something, if you want to know what its mass is, you need to find something that's orbiting it, right? You know that the orbit is going to be based upon the properties of the gravitational force, and the gravitational force is based upon the mass involved, right? Okay, let's do one quick example with this, and let's see if we can measure the mass of the galaxy. So if you look in your book in chapter 6 and you look at the problems and exercises at the end, problem 47 is what we're going to do. We're going to see some interesting things happen when we look at measuring the mass of our Milky Way galaxy. All right, so what this problem says is we can actually measure the mass of the Milky Way galaxy in two different ways. We can just simply point our telescopes at it, we can look at all of the stuff that we see, and we can kind of do some statistics and add up how many stars there are, how much mass there is, and so on and so forth, right? We just look out and we can see how much mass exists in the Milky Way. But then we can also know what we use, what we've seen from Kepler's third law and Newton's law of gravity. We can measure the mass by looking at objects that are orbiting the Milky Way galaxy. So let's do that and let's compare and see what we get. So we have this, observations of the Milky Way indicate a mass of about 8 times 10 to the 11th solar masses, right? 8 times 10 to the 11th of m sun, right? So again, we're 1 m sun, 1 solar mass, is again, as we said before, 2 times 10 to the 30th kilograms. So this is what 800 billion times the mass of the sun is about how much the total mass we see in the Milky Way, right? However, we can do this. We can also measure this mass by looking at stars that are orbiting the edge of the Milky Way galaxy. So we can say we have observed, these are actually real numbers, right? These are, we're not just making stuff up for this problem. These are real numbers that we've observed. This one is a real number for how much observed mass there is. And we can also say we actually have observed stars orbiting the edge of the Milky Way. So we can say a star, whoops, star orbiting the edge of the Milky Way is about 60,000 light years from the center. And it has, let's see, so with a period of about, this should be 60 million. Make sure I get all my zeros right. About 60 million years, right? So you can actually, obviously we didn't wait around 60 million years to see how long it took this star to orbit the Milky Way once, but you can look at stars at the edge of the Milky Way. You can see how far away they are from the center. You can see kind of what their orbital shape is relatively quickly. You can measure how fast they're moving, and then you can extrapolate, okay, so if this star that's about 60,000 light years away has an orbital period of about 60,000 years, what must the mass of the Milky Way be, right? So a star that's this far away, moving at this speed, right, moving around the entire Milky Way in 60 million years, um, right? So I know the Milky Way, we have our galaxy, it's a whole big bunch of stars and whatnot kind of spread out everywhere, but it is a roughly symmetric shape. And so the star on the outside is really kind of orbiting all of the mass that's inside that orbit. And you can actually do some other calculus to kind of really prove this, but you can just take my word for it for now. It is the same if you were to concentrate that as far as the orbital properties of the star are concerned. It's the same as if all of that mass was concentrated at the center in one kind of big ball, versus if it was all spread out in this symmetric way. It doesn't matter. The effectively, you can just say that you can approximate the Milky Way within the orbit of this star, right? Everything that's within 60,000 light years of the center of the Milky Way, as that all of that stuff is the one object that this star is orbiting. And so our equations will still work. So again, this is the observed mass. This is essentially from this we can calculate a mass though, right? We can say, okay, this is how much mass we see. How much mass though must actually be there? And let's see how good we are at our observations. So again, our formula that we have for our mass of the Milky Way in this case will be 4 pi squared over g p squared times r cubed. So let's write down all of our numbers and see what we have. So g is again equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We have R is equal to 60,000 light years. This is equivalent to, if we do our unit numbers, 5.676 times 10 to the 20th meters. That's a lot of meters. Then we have P, our orbital period, as we said before, is 60 million years, or this is about 1.892 times 10 to the 15th seconds. And so with this, right, we can plug all these numbers in. Make sure you do it in your calculator. You can follow along if you'd like. Got to be very careful with all this. Keep track of all your parentheses and your exponents. And what you end up with is you calculate a mass of the Milky Way of about 3 times 10 to the 43 kilograms, right? So this is how many kilograms it is. Let's put it in terms of solar masses. Let's see, we have 1.5 times 10 to the 13th solar masses. So this is actually quite a bit more than what we observed. Why would that be? How much more is it? Let's take this ratio and let's look at it. So if we do the mass of the Milky Way calculated divided by the mass of the Milky Way observed, right? We have 1.5 times 10 to the 13th divided by 8 times 10 to the 11th. What we end up with is a difference of 19 times more calculated mass than observed. So this is actually a problem. What's going on here? Where does this extra mass come from? This isn't just like a small error, right? We're not off by a small amount. If we again, these are the real numbers that we actually have that we can look at, right? These are actually real numbers taken by professional astronomers. If you look at the mass in the Milky Way, you add it all up, you count every single star that you can find. It takes a while, but we have computers that help a lot that can do this. You will see 8 times 10 to the 11th solar masses. But if you look at something orbiting the edge, it's moving way faster than it should be for this much mass. And actually, it's moving so fast that it implies that there is 19 times more mass in the Milky Way than we actually observe. So how could that be? So this is again, this is not just kind of some small error. We're saying that there should be, almost 20 Milky Ways stacked on top of each other that we're just not seeing, right? That would be a lot brighter. There'd be a lot more stuff around. So where does this number come from? What are we actually getting at with this result? This here, again, these are all real numbers. This is actually kind of the first order evidence for the existence of dark matter, right? So if you ever heard that term, it kind of sounds like this weird sci-fi stuff. It is still kind of this mystery, right? But it's actually a very real thing, right? We can very directly observe the effects of it. We know that there is a whole lot of dark matter within this Milky Way galaxy. Some of it you can kind of start to explain away by how much stuff we're missing when we look at this number, but it's not nearly enough, right? There's actually, as it turns out, there is a lot more dark matter in this galaxy and in most galaxies that we found than there is visible matter, right? So this right here, just using our Newton's laws stuff that we've been able to see, this is, and these are the same calculations, that, it's a little bit more sophisticated, right? You make less assumptions, you kind of are a little bit more careful with your numbers, but this is actually about right. This is kind of just like a first order calculation for the initial evidence to show dark matter, right? So this is what we'll end with for chapter 6. I think this stuff is pretty neat, but it's just kind of goes to show you how general these laws and these rules are, right? We started off the chapter talking about, just a car going around a turn, something we've all experienced before. And as it turns out, those same mechanics we can apply, once we know a little bit more about gravity, but those same kinds of rules and laws we can use and we can show and we can start to find evidence for existence of this mysterious dark matter stuff, which we still don't know much else about other than we know it's there. We know it has some sort of gravitational effect on the stuff around it. But past that, it's pretty much a mystery.